In this section, we introduce the concept of an initial value problem. Here we begin with a definition. Let's say I have a function, which we'll call y. We'll treat x as the variable, so y of x. Let's have that be an nth differentiable function. At some particular number, which we'll call x naught. X naught being some specific number, some specific value of that variable x. Okay? In some interval, which we'll call I. And let the values y0, y1, y2, all the way up to yn minus 1. So you're going to have as many of them here. N is the order of the differential equation. So here you're going to have you're going to have this go up to n minus 1. Let's have those be constant values. Solving the problem, that looks like the nth derivative of y with respect to x is equal to a function of x and the first derivative of y and the second derivative of y and all the way up to the n minus first derivative of y, derivative not power, subject to the constraints that the function y, whenever we do solve it, if you plug in this x value, x sub 0, you're going to get this value, which we call y sub 0. And if you take that same x0 and plug it into the first derivative, you're going to get y1. And if you take that same x0 and plug it into the second derivative, you'll get y2. And so forth and so on. And so eventually, if you take the n minus first derivative of your function y and plug in that exact same x0, and that is important here. It does have to be the same number each time that you're plugging in. That should give you this final constant value y sub n minus 1. Okay? Solving this problem, subject to these constraints, is what's called an nth order initial value problem. Like many things in differential equations, you will have long titles here. This is a long thing to write and a long thing to say. So oftentimes the expression nth order initial value problem is abbreviated as IVP, initial value problem. The nth order part is sort of implied by the problem itself, by the equation, where the n constraint equations, this first equation, second equation, third equation, all the way up to this one, where the n constraint equations are called the initial conditions. Sometimes abbreviated IC for initial conditions, like that. So for example, x equals c1 times the cosine of t. Here x is the function and t are the variables. Often we'll have x as the variable and y as the function, but of course those are just labels. Here we're going to treat x as the function and y and t as the variable. So x equals c1 cosine of t plus c2 sine of t. This is a two-parameter family of solutions. for the equation x double prime plus x equals to 0. So assuming we have a problem like that, then what we call the initial value, or rather the solution to the initial value problem, then the solution to the IVP, which is given by, and again, the initial value problem is given by an equation and the constraints. It's not just enough to have the equation. So the solution to the IVP, that is x double prime plus x equals 0, subject to x at pi fourths equals root 2, and x prime at pi fourths, and notice it is the same number for both that you're plugging in. You say, does that mean it's not possible for these to be different numbers? It is possible for them to be different numbers, but then that's not called an initial value problem. Those are called boundary value problems, and we talk about those much later. They're more complicated. So here, x at pi fourths is equal to root 2, and x prime at pi fourths is equal to 2 root 2. Okay, so this equation, along with these initial conditions, are what we call the initial value problem. Okay. And when we say we're solving an initial value problem, what we really mean is, okay, here's the set of solutions. Here's a set of the two parameters family of solutions. Now, to solve the initial value problem, we want to find one particular member of this. So there's two numbers that we're looking for. We're looking for a particular solution out of all of these members of this family, such that when you plug in pi fourths into the original function, you're going to get root 2. And when you plug it into the derivative of that original function, you'll get 2 root 2. All right, so let's give that a try. C1 cosine of, that t is going to be replaced by pi fourths for the first one. So pi fourths plus C2 sine of pi fourths. Like this. And what this initial condition says is when you plug that number into that solution, you're supposed to get root 2. Okay, when we get root 2. Now, of course, these two numbers can be simplified. Cosine of pi fourths and sine of pi fourths are both root 2 over 2. So really, we can write this as C1 times root 2 over 2 plus C2 times root 2 over 2 is equal to root 2. Okay? And in fact, notice that root 2 is a common factor for all three terms. So I think it'll be even easier if I just divide everything by root 2. So really, I just get half of C1 plus half of C2 is equal to just 1. And in fact, I can go even further, right? I can say, well, go ahead and double both sides, and that'll be C1 plus C2 equals 2. Of course, all of these are the same thing. They all mean the same thing, but I feel like this one's going to be easiest to work with because numbers are the easiest there. All right, so here we want to find C1 and C2 so that they add up to 2, because that will satisfy this equation. That'll satisfy this condition. Well, yeah, but there's lots of combinations of numbers that add up to 2. But we're not done. Now let's go ahead and consider the derivative of x. Okay, so the derivative would be, well, let's actually go ahead and take the derivative. Derivative of cosine of t is negative sine of t. So here we would have negative C1 sine of t plus, and then the derivative of sine of t would be cosine of t. So it would be C2 cosine of t, like this. And that would be x prime. But we're supposed to take x prime at pi over 4. Okay, so let's plug that in, pi over 4. And same thing here, pi over 4. And that's supposed to equal to, when we do that substitution, we're supposed to get 2 root 2. Okay, so, well, again, these are both going to be root 2 over 2, except now that one's got a negative. That's going to be negative C1 root 2 over 2, plus, and that one's still a positive, C2 times root 2 over 2, and that's equal to 2 root 2. Just like before, it's probably easiest if I go ahead and divide out by root 2 on everything. That'll leave me with negative half C1 the root 2, I divided it away, plus 1/2 C2. Again, the root 2 has been divided away. And then here, if I divide away the root 2, I'm just left with 2. And it's probably better if I go ahead and just double everything now. So this will give me negative C1 plus C2 is equal to 4. So now what do I have? I have two unknown values. I need to figure out my C1 and my C2. And I have two equations that involve those two unknown values. It's a system of equations. Go ahead and solve that system. So now we solve the system where C1 plus C2 is equal to 2. And negative C1 plus C2 is equal to 4. This is simple enough. I can just add the two lines together. If I add these two lines together, C1 plus negative C1 cancels out. C2 plus C2, that's 2C2. And 4 plus 2 is going to give me 6. And I'm jumping ahead of myself here, divide both sides by 2, and that'll give me C2 is equal to 3. So I find my value of C2. Now coming back to either of my original equations, C1 plus 3 is equal to 2, or I could plug it in over here. I could say negative C1 plus 3 is equal to 4. Either way, we get C1 is equal to negative 1. So here we have a two-parameter family of solutions to this equation, and any pair of numbers will make it work as a solution. But if you take that solution and pair it with these conditions, then not any values will work. In fact, there's only one particular set of values that'll work. Right here, C1 must be negative 1 and C2 must be 3. So what we call the solution to the initial value problem, so the particular solution, that's say the solution to the initial value problem that we've been looking at, is going to be that solution that we already had, but with the specific constants in place. Which does suggest that to solve a initial value problem, you first have to find the parameter, the n parameter family of solutions, and then substitute. That's not always true, especially in application. But for now, that's the way we're going to approach it. We're going to approach it as if we will have to find the family first and then specify the values. We'll see later that that is a method, but that's not always the only method. So here the particular solution would be x equals, my C1 is negative 1, so I'd have negative 1 cosine of t. And then my C2 is 3, so I'd have plus 3 sine of t for my initial value problem. Okay, let's consider another example of this. This one will have a slightly different looking result, and will suggest something about solution curves as we've discussed previously. So, for example, consider the equation y equals 1 over x squared plus c. So this is just a one parameter family of solutions. There's only one unknown constant. Okay, so this is a one parameter. It would help if I learn how to spell. Family of solutions. For the equation y prime plus 2xy equals 0. Okay. Now let's consider the initial value problem. Y equals 1 over x squared plus c, subject to the condition that y at 0 should equal to negative 1. Y at 0 should equal to negative 1, like that. Okay? Well, then finding a single solution to this initial value problem is relatively straightforward. We don't even need to take any derivatives here, right? We're simply plugging in 0 into our function with a end result of negative 1. So here this would give us, let's see, if I plug in 0, I get 1 over 0 squared plus c, and that's most equal to, well, the y value, when I plug in x equals 0, should be negative 1. Okay, well, that's just going to be 0 squared is 0, so that just disappears, giving us 1 over c equals negative 1. and so c must equal to -1. Okay, so then I would get a solution to the initial value problem. The solution to the IVP is going to be 1. Oh, I should write that as y equals 1 over x squared plus a -1, or I'll just say -1. Okay, so there we go. Here is our solution to our initial value problem. Now, consider the solution curve of this thing. Say, well, I can graph this. This is one of those things that I remember from algebra, right? I could factor this denominator. I could write this as y equals 1 over x plus 1 times x minus 1. And because 1 and -1 are zeros of the denominator, that means I'll have vertical asymptotes at 1 and -1. So when x equals 1 and x equals -1, I end up with vertical asymptotes. And then I could plot some points. Right? If I plugged in x is equal to 0, I would get 1 over -1, which is -1. So down here, if x is 0, y is -1. If x is, well, I can't plug in 1 because that would give me an asymptote. That's undefined. So I'll plug in 2. 2 squared is 4. 4 minus 1 is 3. So if I plug in x equals to 2, I get 1 over 3, so a small positive number. And same thing for -2. -2 squared is 4. 4 minus 1 is 3. So if I plug in x equals -2, I get positive 1/3. And if I plot some more points, or if maybe I look at concavity, if I want to do some Cal 1, whatever, I end up getting this graph. Okay. But as we have seen before in the last section, if you have a solution to a differential equation, whether it be an initial value problem or not, it has to be n differentiable. Right? It has to be a function whose derivative I can take, or whose nth derivative I can take actually, which means it must be continuous. And clearly this thing is not continuous. Okay, but in the last section we also saw that, well, we can just pick a piece, right? There's 3 pieces here, so just pick one and that'll work, right? Well, if you're given no other information other than I'm trying to solve this problem up here, trying to solve this problem right here, and I find that this is a 1-parameter family of solution of this problem, then yeah, all 3 of these are equally valid, and so I could just pick one. But that's not the case anymore, because whatever solution I have not only has to satisfy this equation, not only does it have to be on this curve, but it also has to meet this initial condition, which means that when I actually graph this thing, the solution curve must be continuous, sure, but it must also contain the point 0, -1. So here, because of the initial condition, the solution curve must be continuous and contain the point when x is 0, y is -1. Okay, so then I can't just pick one. It has to be specifically this one, the one that contains the point 0, -1. So if I were to ask for the solution curve, I would want only this piece right here. Only this is the solution curve. So an initial value problem is satisfied not just by solving the equation, but also it must contain the initial condition or conditions to be a valid solution. Note that solutions to initial value problems, although clearly there are fewer of them than there are just regular ordinary differential equations, the initial condition narrows it down to fewer solutions. Here, the last couple of examples make it seem like there's only one solution. That's often the case, but it's not necessarily the case. So here as a quick note, although it is common for it to be true that there's only one solution, that doesn't have to be true. There may be multiple solutions to an initial value problem. And as a very quick example of that, we'll just show one that has two. If you have xy prime is equal to 2y, subject to the initial condition that y at 0 should equal to 0, you have two solutions to this. This has y equals x squared and y equals 0 as solutions. Because after all, if I plug in 0 into this, 0 squared is 0. If I plug 0 into this, 0 is equal to 0. Okay, so both of these satisfy this initial condition. But also, if you plug them into the differential equation, x times 0 equals 2 times 0. Yeah, that's clearly true. If I plug this one in, I get x times the derivative of x squared. So x times 2x, that's 2x squared. That's going to equal to 2 times x squared. Yeah, 2x squared equals 2x squared. That is correct. So both of these are perfectly valid solutions because both of them satisfy the equation and both of them satisfy the initial condition. So there may be more than one solution to this. Okay, but then doesn't that kind of cause a problem? Because if I'm trying to solve an initial value problem, how do I know if I'm done? If it only had one solution, then that would be great because once I find a solution, that's it, I'm done. But if it has multiple ones, how do I even know that? Maybe if I try to solve it, I find one easily and another one is very difficult to find and I don't even realize it's there. Well, there's a theorem that can help us narrow it down. So theorem. Let's say, actually this might be a little bit big for this space. I might not fit it all in. Let's move to the next page here. All right, so theorem. Let's say you have a rectangular region. We're going to call it R. Let R be a rectangular region in the xy plane. That is defined by x bound between two constants, which we'll call a and b, and y also bound between two constants, which we'll call c and d. That contains a specific point of interest, which we'll call x naught, y naught. That contains a point, which we'll call x naught, y naught. And it should be inside the rectangle. We don't want it to be on the edge or anything. So let's say on the interior of the rectangle. Let's not have it on the boundary. On the interior. Okay. Now let's have a function f be defined on that R. In other words, you can take any point inside that rectangle and plug it into your function. So let f of x comma y, obviously it's a point, so you can plug in both the x and the y. So let f of xy be a function of two variables that is defined on that region R. Any point inside the rectangle R is something you can plug into the function. Now if f of xy and the partial derivative of f with respect to y, if those are both continuous, at least as long as you're inside of R, if there's any discontinuities, they should exist outside of that rectangle. Then there exists some interval which we'll call I sub 0 or I naught. There exists some interval I naught, which is a small variation on your x naught, on the x value of your points. So we'll say x naught minus a little something, and all the way up to x naught plus a little something. X naught minus h, x naught plus h, for some positive h that is contained in the interval from a to b, the interval that, so it's inside the rectangle. Contained in the interval from a to b. It's contained inside the boundaries of the rectangle. And a unique function y. Then there exists, and a unique function y of x that is defined on that I, defined on that interval, that is a solution to the IVP. So this guarantees you do have a unique function that works that way. In other words, a unique solution. Problem. Dy dx is equal to f of x comma y, subject to y at x naught is equal to y naught. So for example, we asked, does there exist a unique solution to y prime equals the square root of y squared minus 9, subject to y at 5 equals to 3. Or at least, does there exist a unique solution, at least according to our theorem? Yeah? All right, so here we have the derivative of y is equal to a function of xy. The derivative of y is equal to a function of x and y. Technically, the x is set equal to 0 since it doesn't exist here. Oh well, that's still technically a function of x and y, even if the y is equal to 0, yeah? Okay, so f of xy is that square root of y squared minus 9. Okay. So if you take the derivative of that function f with respect to y, for those of you who've taken Cal 3 already, you're familiar with this notation. If you have not taken Cal 3 and you're not familiar with this notation, suffice it to say that what it means is if you have multiple variables, you're going to consider just the one in the denominator. You're going to consider that one as a variable, and everything else you're going to consider it as if it were a number. Even if it looks like a variable, you treat it like a number. In later parts of this course, we'll take a look more closely at partial derivatives, in particular when we look at partial differential equations. They won't be a central focus of this course, but they show up often enough that we'll give a little more practice and some better definitions later. For right now, though, it's not even necessary because, well, since there is no x in this problem, here it's basically just a regular derivative of y. Okay? But if you're not familiar with this one, you may wish to look this one up before we get there, or if not, we'll go over the details of partial derivatives a little bit better in a later section. All right, so the derivative of f with respect to y, okay, well, there's no x here, so this is just like a regular derivative. Well, let's see, the derivative of a square root is 1 over double that root. But then the chain rule says to multiply by the derivative of the inside, which would just be a 2y. My 2's would cancel out, and I would get y over the square root of y squared minus 9. Y squared minus 9. And now, you'll notice that both the original function, the f of x, y right here, notice that the original function f of x, y and the derivative of that function with respect to y are continuous as long as your function doesn't have y values that are between -3 and 3. Right? Because if you have something that's between -3 and 3, you're for example, you have 0, you'd end up with the square root of 0 minus 9. Square root of -3, that's imaginary. We're not dealing with imaginary numbers. Everything's real. Same thing if you plugged in 1 or 2. Right? Now, technically, you could plug in 3 right here because 3 squared is 9, minus 9 is 0. Okay, that's fine. But you wouldn't be able to do that here because here you would end up with, well, you'd end up with 3 over 0, which is still undefined. So, these are undefined between -3 and 3. Again, this one does technically allow for -3 and +3, but this one doesn't. Okay, so both my function and my derivative of my function with respect to y are defined and, in fact, continuous, outside of the interval from -3 to 3. So we can say everything from -infinity to -3. Again, don't include the -3 because that one won't allow it. And also everything from 3 to infinity. Okay, so it's continuous as long as you're in there. Visually, what that would look like is, let's see. Yeah. So visually, what that would look like is you would want, now of course these are bounds on y, so you'd want y to go from 3 to infinity. So here's y equals 3. And anything above that. Or here I would have y equals -3 and anything below that. Okay, so my function and its derivative are continuous as long as I'm either here or here. Okay, so for our theorem, we have a rectangular region in the xy plane. Well, here either of these would satisfy because this is a rectangle. Mind you, it's a rectangle that goes on forever, but it's still a rectangle. Same thing for this one. Oh, right, but you're supposed to have just a single rectangle. Oh, okay, well, pick one. Either of those would work. So as long as our initial condition is inside of either of those, then the theorem says we're guaranteed a unique solution. Okay, however, since, well, let's see, what is our initial condition? Our initial condition, x is equal to 5 and y is equal to 3, so 5 comma 3, that would be right about here. That's not inside of either of those regions. Remember, it has to be properly on the inside, on the interior. So since our initial condition 5,3 is not contained on the interior of either rectangle, it's on the edge of one, but that doesn't count. It's on the should be on the interior of either rectangle, then we are not guaranteed a unique solution. Maybe there is, but we don't know. We might end up with multiple ones. Now, what would guarantee a unique solution is if the initial condition had been inside of either of those. It wouldn't really matter which one. So here, note, it would guarantee a unique solution if the initial condition was changed to be in either plane. Was changed to be in either plane. So for example, I don't know, 1 comma 5. So y at 1 equals 5. There we go. That would be corresponding to the point 1 comma 5. And 1 comma 5 is definitely inside of this rectangle. So if this initial condition were used instead of this one, then yes, the theorem would guarantee we had a unique solution. So that's it for the section, and that's it for now. If anybody has any questions, please reach out, and I hope you all have a nice day.